Momentum is the total quantity of motion. Impulse equals change in momentum. And as you'll see, this comes straight out of Newton's second law, which makes me mad. So mad that I want to punch a wall. But if you ever punch a wall, make sure you put on a boxing glove first. You might hurt your wrist. Here, let me explain why. We'll start by saying that for these two collisions, and it's all about collisions in this chapter, for these two collisions, the momentum of the hand is the same. Now, momentum is equal to mass times velocity. So we'll say that this is a light boxing glove and it's not slowing you down, or in any way, the product of mass times velocity is the same whether you're wearing the glove or not. But when you hit the wall, the velocity of your hand goes to zero. Your hand will say stops when it hits the wall. It's not like you're busting through the wall. Your hand's got to stop at some point. And when it does, the final momentum of your hand will be zero. That means that the change in momentum of the hand is the same in both cases. And that means that the impulse is the same in both cases because of what I said earlier. Impulse is equal to change in momentum. J is equal to delta P. Impulse is equal to change in momentum. So the impulse is the same, and we know something about impulse. We know that it involves time, and the time is longer for the boxing glove. That's the key. The time is longer. It still takes less than a second for your hand to come to rest, but there is a longer time that your hand spends decelerating. If you sit down on a cushion, it'll come to rest pretty soon, but it'll take a longer time than if you sit down on a stone. Bubble wrap is all about time. It's all about time. That's the key thing here. Time is longer when you hit with a boxing glove, and that means that the force is smaller. The force is smaller because J is equal to Ft. Impulse, and the impulse was the same. Impulse is equal to force times time. So you either have a bigger force and a smaller time, or a smaller time and a bigger force. Like consider an egg falling on a plate. Here we have a force versus time graph. And as you can see, it's a really big force for a really short amount of time. This is like sitting down on a stone, a big force for a short amount of time. Same egg, same mass, dropped from the same height, but this time on a pillow, and a different force versus time graph. Here we have a smaller force, but it's spread out over a longer amount of time, saving the egg. We're saying that the impulse is the same, so the same area, it's the same area. I hope I drew this right. The same area under this force versus time graph, the same area shaded region, but a totally different effect for the egg. Speaking of totally different effects, consider a bus screaming down the highway and it hits into a bug. The bug splatters on the windshield of the bus. Sorry to use a violent example here, especially for the bug. We'll start by saying that the force of the bus on the bug is the same magnitude as the force of the bug on the bus. That's thanks to Newton's third law, of course. And we also know that the impulse is the same. The impulse is the same because impulse is equal to force times time. It's the same force. It's the same time. The time for the collision is the same. Impulse is equal to force times time. And if impulse is the same, then the change in momentum is the same for the bus, and the change in momentum is the same for the bug. Also, now we're considering a bunch of different things. We're considering that this bus is coasting down the highway and we're ignoring air resistance. So this is a totally unrealistic example here, but just picture a bus coasting down the highway without stepping on the gas or stepping on the brake, and it hits into a bunch of different bugs. Again, it's kind of gross, but eventually that would slow down the bus a little bit if it hit into too many of these bugs. Anyway, the change in the momentum is the same for this collision. Has to be, because impulse is equal to change in momentum. But speaking of momentum, the momenta are very different because the bus has a huge momentum as it's screaming down the highway. Not in this picture. I know that this picture, the bus is at rest, and anything at rest has zero momentum. But the bus moving down the highway at highway speeds, big mass, big velocity, big momentum. The bug just kind of hovering there, small mass, small velocity, small momentum, which means that the acceleration of the bus is very small, the change in velocity of the bus is very small, and the change in velocity of the bug is very big. Velocity and momentum, totally not the same thing. We have the same change in momentum. The same change in momentum for the bus and the bug, but that change in momentum looks very different. For the bus has so much momentum that the change in momentum doesn't really affect it at all, but the bug has so little momentum that its change in momentum really does have an effect on the bug. The acceleration is very big for the bug, very small for the bus. But enough about buses. How about a rocket? Here on the left, we have a rocket that's not firing the engine. On the right, the rocket that is firing the engine, and this rocket, we'll say, is way out there in space, so far away from any planet or star that there are no forces acting on it, not even the force of gravity, which is really impossible, but we're just trying to isolate and just trying to focus on this rocket here. So for the rocket on the left, we'll say there are no forces. For the rocket that's firing, we'll say that the force of the rocket on the exhaust is equal to the force of the exhaust on the rocket. Again, it's a Newton's third law type of situation going on there. The force of the exhaust on the rocket equals the force of the rocket on the exhaust. And there's no exhaust for the rocket that's not firing, but the rocket that is firing, the momentum of that exhaust is down and to the left. Momentum is equal to mass times velocity. Individual exhaust particles are pretty small mass-wise, but they're moving pretty fast velocity-wise. The momentum of the rocket is to the right. The momentum of the rocket, again, is equal to mass times velocity. And the momentum of the rocket is to the right. And rockets work in space for this reason. Rockets work in space. Airplanes would not work in space. No air to push off of. Helicopters would not work in space, but rockets sure do. So these situations look totally different. In one case, nothing's going on. In the other case, you got exhaust being fired in one direction and the rocket moving in the other direction, only they're not so different because in both cases, the total momentum is zero. The total momentum is zero, which is easy to see when nothing's moving, but the total momentum of the rocket on the right is also zero. The momentum of the exhaust balances the momentum of the rocket. Momentum is a vector quantity. And how do we know that? Because impulse equals change in momentum, and there are no external forces on this system. And you hear that and you're like, no, wait, that can't be true. There has to be lots of forces, a huge force acting to get this rocket to move. And yes, there are. There are large forces. There are internal forces, internal to the system. There are no external forces acting on this rocket. So momentum, change in momentum is equal to impulse, no external force. No impulse, no change in momentum. In both cases, the total momentum of the system, the whole system, is conserved. More on that, much more on that later. First, let's drop the ball. And it matters. It matters if it's a bouncy ball or a ball of clay that just lands and thuds. And we'll say it's not really clear from the picture here, but we'll say that the bouncy ball on the left is rebounding to the original height. So no loss in energy whatsoever from the collision. It rebounds. This is like a picture of it rebounding up to the original height. And we'll start by saying that the initial momentum is down. Momentum, as we said, is a vector quantity. Direction matters. So the initial momentum is down. The final momentum is up. If you're a bouncy ball, the final momentum is zero if you're that ball of clay. And next, a controversial statement. I'll say that the change in velocity is bigger for the bouncy ball. The change in velocity is smaller for the clay ball. Now, that might seem kind of strange if you're thinking about the speeds. We said we'll just say that the ball is landing. It's traveling at 3 meters per second while it lands, and then it rebounds at 3 meters per second. The clay ball is landing at 3 meters per second, and then it has a velocity of 0. So it might seem strange to say that the change in velocity is bigger on the left because there's no change in speed on the left. But yes, speed and velocity are totally not the same thing. Velocity includes direction. So we'd say that the change in velocity on the left is 6 meters per second, and the change in velocity on the right is 3 meters per second. From -3 to 3, that's a change of 6 meters per second. In both cases, though, the impulse is up. Impulse is equal to force times time. Impulse, the force from the floor on the ball. The impulse on the ball. The impulse, the normal force from the floor on the ball pointing up, perpendicular to and away from the floor. The impulse is up. And impulse is equal to change in momentum. And we'll see from those velocities that the change in momentum is twice as great on the left than it is on the right. Impulse equals change in momentum. So pretty simple statement to make, but as you can see, as everything with physics, there's lots of different ramifications of that statement, and we'll get to the big one, the law of conservation of momentum, which states that momentum is always conserved unless it's not. The law of conservation of momentum says that momentum is conserved unless the system is acted upon by an outside force. And you can tell how I emphasize that word, the system is acted on by an outside force, that's the key, and that's the tricky concept to get here. And we'll consider that by looking at videos of balls bouncing into each other. And what happens after they collide? Well, lots of things can happen. It matters that velocity is a vector. Our first collision, ball 2's at rest and ball 1 hits into it. And then ball 1's at rest. This is kind of like a pool shot that you might have tried to do in a game of pool. Momentum before the collision is equal to momentum after the collision. Here's another collision. Ball 2's at rest. This time they stick together. Same sort of thing though. Momentum of the system before the collision equals momentum of the system after the collision. Here's another collision. This time ball 1 bounces off of ball 2. And it's a very different type of collision, but the law of conservation of momentum holds. No external forces on the system. Ball 2 feels a force. Ball 1 feels a force. And therefore we have conservation of momentum. This time ball 2 is moving and ball 2 wins the collision. They stick together. Ball 2 had more momentum than ball 1. Here they bounce off of each other. This can be kind of hard to understand exactly what's going to happen. One thing we know that's going to happen, though, is that the momentum of the system before the collision is equal to the momentum of the system after the collision. Here we have ball 1 and ball 2 hit together and stick together. And we know that they both had the same amount of momentum before they hit together because the momentum of the system after the collision is 0. That's clear. You can see, this is the same situation if you run the videotape forward or backward. Either two balls come together, hit together, and stick together, or you put a little spring between them and the two balls shoot away from one another. In either case, the total momentum of the system has to be 0. This is all very qualitative, though. Let's try to get quantitative with this situation with an applet. Here we have two balls, the red and the blue. They're going to collide in a head-on collision. We'll give ball 1 a mass of 4 kilograms, ball 2 a mass of 6 kilograms. We'll give them the initial velocities shown here. And we'll start with an inelastic, a sticky collision. Let's see what happens. And boom. They collide together and stick together. Looks like ball 2 won this collision just a little bit. And we can quantify that little bit by using the law of conservation of momentum. We'll find the total momentum of the system of both balls before the collision. The total momentum of the system before the collision is negative 2.0 kilogram meters per second. And that equals the total momentum of the system after the collision. The total momentum of the system after the collision is still negative 2 kilogram meters per second. And following through the math, we can find the final velocity of these two stuck together balls is negative 0.2 meters per second. The math here all revolves around that idea. Impulse is equal to change in momentum. And here the impulse on the system was 0. No external forces on the system. No change in momentum of the system. The momentum of the system before the collision is equal to the momentum of the system after the collision. We'll try it one more time, this time with a elastic, a bouncy collision. We're changing it to an elastic collision here. Otherwise, the same mass, the same initial velocities. Boom! Collide these guys together and see what happens. Boom! They're bouncing off one another, and this is pretty exciting stuff. And I'm not sure, how would we find those final velocities? I'm not sure, but plugging them into our equation, we see with a final velocity of negative 4.4 for the red ball and the final velocity of 2.6 for the green ball. It is true, the hype is real. The momentum of the system before the collision is equal to the momentum of the system after the collision. One last thing before we go, and that is this button here, the center of mass button. The center of mass of the system. Center of mass, what is that? Well, we'll think about the center of mass and we'll let this collision happen. The center of mass, that little X there, is moving and moving and moving and moving and moving and moving. The center of mass, for this collision at least, did not seem to care about the collision. And here's another, this time an elastic collision, and we'll let that happen. And the center of mass is moving with the same velocity, the same constant velocity to the left before and after the collision. And this is a really big deal. This is Newton's first law. I said earlier that this Ft equals m delta v stuff, this all came out of Newton's second law. Well, this conservation of momentum stuff comes right out of Newton's first law. An object in motion will remain in motion unless acted upon by an outside force. Turns out the same thing is true of this system. A system in motion, the center of mass is moving to the left here. A system in motion will continue in motion unless acted upon by an outside force. But how are we going to find those final velocities? More on that in the next chapter.